Okay, so first, thank you for the organization, for inviting me, and I think for putting together this very nice meeting. So I'm going to talk about multiconfigurational DFT, and I'm not the first person to work on this. And actually, one of the most common questions I get from people / reviewers is, why do you think yours is the correct one? And this is a very difficult question to answer, so I often go into this formal properties and things like this, and it's very difficult. And it's so difficult because there is no benchmark comparing different ones. And now I found sort of this much nicer answer, which is to say, mine is the correct one because all of the other ones are a subset of mine. And that's what I'm going to try to justify here. So the outline is first going to justify why strong correlation, why we're interested in this, and then why does DFT perform or not perform for strong correlation. Then we can make this sort of wish list. What are the properties we would like to have in our multiconfigurational DFT? And then go through the history of these different versions that have been proposed over time and how do they fulfill or not this wish list and how we can revise them to make them fulfill the wish list a bit more by merging them together. And finally, some benchmarking finally of these different variants. So strong correlation, you have, I suspect all of you seen that at some point in your life. You break H2, and you have, at short distance, dynamic correlation, and towards infinity, you have what people call static or non-dynamic, or now I would call strong correlation. And it's basically just a symptom of the fact that those two extreme cases you can qualitatively well describe with a single determinant, but you can't really merge those two smoothly. You can't go from the left to the right within a single mode in a smooth way. Okay, so most of you have seen this. You all know this issue, and then you forget about it because you don't dissociate H2 anymore, and that's fine. But fun fact, there's a lot of things which don't look like H2 dissociation, but which actually are in some ways. And among my own interests, one example would be transition metals, and especially if you have these two antiferromagnetically coupled metals. So you would describe this as a spin up on one side and spin down on the other side. But that's just a stretch iron-iron bond. If you think of it as a stretch bond, yes, H2 at infinite distance, you say it's one spin up here and one spin down here. So this is exactly what you're saying when you're making this graph. But of course, they're not at infinite distance here. They're far from it. They're still interacting. So this is a clear strong correlation case. And then, and this is almost a cartoon, so it's not really scientific, but just to illustrate the concept, when you have excited states crossing, you have this sort of same thing when you're going from one configuration to the other one, and in between, it's sort of question mark what's happening here. So those are all cases where you would like to use this probably multiconfigurational method. And again, to illustrate the diversity of cases, this is the keywords. It's a word cloud of all the keywords of papers citing MOLCAS, which is a good indication of what people are using MOLCAS for, and therefore what using MTSCF for. And you can see that there is not much H2 here. It's sort of ground state excited state. There is magnet here, so like spin properties. There is X-rays, there is ligands, so there is metal complexes, so there's a lot of things. So okay, strong correlation is important. I hope I have convinced you of that. Now I would like to use DFT, because DFT is cheap. And does DFT work for strong correlation? Most people would say no. And when you ask them why, it's because DFT is a single configurational method. But that's not really true, because the Concham wave function is not meant to be the function of the system. It's just a tool that you're using to get the densities. There is nothing saying that DFT is single configurational. And to actually illustrate this, I will create this new property, which I call the bond-breaking consistency. And I mean, you see, it's not a very new property in some sense. If you have two open shell fragments at infinite distance, the energy that you compute should be the same as if you compute them separately. And that's basically just the standard size consistency, but specifically for open shell. And adding this thing that I don't want to do symmetry breaking, because symmetry breaking has its own set of issues, and I don't want to go into this. And if you define this property, you see that DFT fulfills this, no problem. And you can prove this in 3 lines. Energy of 1 and 2 at infinite distance is, by definition, the function of the density. It's not fully trivial, but the density will be the density of each subsystem separately. And then if your functional is reasonably local, meaning that 2 densities at infinite distance don't interact, then you will get that it's just the sum of the two functionals, and that's just E1 plus E2. And of course, we know that we're actually using very local functionals, because we're using typically LD and GGA, so we definitely fulfill this. So DFT should break bonds, no problem. Okay, well then you try it, and you're disappointed because, well, B-lib curve surely is better than R3-Fock, but it's not going to zero, so it's not getting the same energy as the two fragments separately. So what's wrong? Is it my math before, or is it this calculation? Well, what's wrong is that B-lib is not a spin, is not a functional, density functional. It's a spin density functional. And that makes the entire difference. And you can see it again by changing this constant from before. So now we have the two densities, alpha and beta. And if I forbid to use symmetry breaking, those two are simply half of the total density. Again, I'm using locality, so it's now subsystem 1, subsystem 2, fine. And that's not equal to the way you're computing each fragment, because each fragment, you're doing it with spin projection. So again, if you do H2, you don't do H with half of a spin up and half of a spin down. You do H with a spin up only. Meaning that the spin densities are not the same, unlike what you do in the H2. So this is why now we have this strong correlation problem. So all the strong correlation and this single configuration behavior of DFT is because we're using these spin densities. And so this is one of the issues of spin density, so this improper description of bond breaking. It's not the only problem. When you use spin, you also have the problem with spin multiplets. So the the triplet should have three components, ms equal -1, 0, and 1, corresponding to 2 spin up, 2 spin down, and then the in-between one. And the 2 spin up and 2 spin down are well described by spin DFT, but the in-between one is not degenerate with the other two in DFT. It's degenerate with a singlet, which is of course completely wrong. And why do we do this? So why did we introduce spins then in the first place? Well, it's because it gives a good description of the exchange energy. The exchange energy in Hartree-Fock, which is how we think of exchange energy, it's electrons interacting with the same spin electrons. And this can be put very easily into place by saying it's a function of alpha density plus function of beta density. So this gives immediately a good description of the exchange energy. And also it really helps distinguishing between spin multiplicity. So the density of a triplet and open shell singlets are very similar. So it's difficult for the functional to distinguish them if you don't add the spin on top of that. So we all chose that it was better to have this compromise property as long as you're doing correct exchange energies. But that means that now DFT has become single configurational, and if we want to do better, we have to do multiconfigurational DFT. And that's, of course, where I'm finally going. So we're going to do multiconfigurational DFT. What do we want it to do correctly? There's many properties we might want. We might want it to be formally exact. It doesn't really help us knowing how to work it out, but it's nice to know that it is exact. And for multiconfigurational DFT, one issue is, what does it mean? Does it mean exact if your active space becomes full CI? Or does it mean exact at every active space? Should it actually converge to full CI? So should it, by construction, should it give the full CI result if your expansion is the whole full CI? You would want it to be variational because it helps with computing properties, and also because MC-SCF is variational, DFT is variational, so there's no reason why the mix of them should not be variational. And you would ideally want it to be equivalent to Concham DFT for a single determinant. So those are a bunch of properties that we are not going to use because they don't really lead to anything interesting. So in sense, you can always kind of prove them to be okay. If it's not variational, you can make it variational. If those two are not fully, like, you can make it work. So instead, what we're going to use is those other properties, that it should be bond breaking consistent, so what I defined earlier, that at infinite distance it reaches the right limit. It should correctly describe spins, because as I mentioned for DFT, there's a sort of a trade-off between describing bond breaking and describing spins. And it should be free from double counting, which means that if you are having MC-SCF plus DFT, you don't want to count the correlation in both of them. And it would be nice if it gives good results also. So now let's go through the historic very quickly. The very first suggestion was in 1974, so really nothing new here. And it was simply to add to the MC-SCF energy the correlation energy from DFT. And this is very easy. it actually does bond breaking correctly because they didn't add a spin density. It was really a function of the density only. And that was really the point of this paper, was really to do bond breaking correctly. But it doesn't describe spin, and it has double counting. And actually, this is when this double counting was sort of phrased, because like, okay, now if you have MC-SEF and we increase like this space, it will count all the correlation already. And of course, they answer that by saying, don't increase like this space, just use the smallest one you can. But this is not really viable for a long-term strategy. But this is okay starting point. And after this, all of the quest of this field has been, how do you remove double counting? This is really what everybody has been focusing on. And so there have been a lot of suggestions. The first category, and it has been worked by a lot of people throughout the years, and nowadays it is the group of Katarzyna Pernal doing this CAS-PDFT, as I'm calling it. And the idea is to use the on-top pi density to measure correlation already included in the active space. So the on-top pi density is probability of having two electrons in the same place. And so this is a direct measure of correlation. So you can use it to know how much correlation you have already included and use this to scale down the DFT correlation after that. A second idea, which started by Savin in the 90s and now is worked by Eric Hedegaard in Delcey quite a lot, is this range-separated hybrid. So using MC-SEF and DFT, but MC-SEF describes only the electrons when they are far apart, and DFT the electrons when they are close together. And that's very intuitive because electrons close together, that's dynamic correlation. That's what DFT is very good at. But when you're doing bond breaking, this is more for long-range thing. So it's sort of reasonable. And finally, you could also treat it as a double hybrid. So you could say that you have MC-SEF, a fraction of it, not all of it, and then you scale down the exchange and the correlation. Now, this formula is actually quite interesting because most double hybrids will also scale down the correlation by a factor of 1 minus lambda. But they show that because if you're optimizing wave function variationally, because the correlation is to second order, it's at least second order and beyond, the scaling should be lambda squared. And that's quite nice because this formula has one issue. This prevents double counting, but it can also underestimate, because if you don't have any correlation in your MC-SEF, well, you're still scaling down your correlation, your DFT correlation. So you would be essentially missing correlation. But because it's only a lambda squared, if your lambda is, let's say, 20%, which is a standard DFT ratio, then you're only missing 4% of the correlation. So it's sort of nice because of this. Anyway, so these are all three things that have been proposed. And if I summarize the property of all of this, so first, CAS-PDFT, it does bond breaking correctly, fine, because it doesn't have any spin densities. And it should not do double counting because they have a functional for that. But we don't know, of course, how good this functional is. So I put a question mark here. And it might not do spins, and I will see that, I will show that very soon, why. But all the other ones, we started from this MC-SEF plus DFT, which clearly has double counting. And then the range separation removes double counting completely, and this one parameter hybrid, this double hybrid type, it removes double counting, but 4% error might be there. But it's a small error, so we put it as orange. It's up, but it's orange. On the other hand, bond breaking and spin are still a trade-off. Either you use a function of the density only, like the first scheme, and you do bond breaking but not spin, or you use a spin density functional, and then you do spin but not bond breaking. So all of these other hybrid versions here did not necessarily do bond breaking correctly. Okay. So now that's where the revolution happens, and this is this MC-PDFT. And that's a completely different framework, because instead of starting from MC-SEF and trying to add correlation, we're going back to, okay, why did DFT fail in the first place? It was because of these spin densities, we said. So we need something else. So density only is not enough. We need some new variable, but not the spin, because that's clearly not working. And so the idea that they suggested was to use the on-top pi density. Why? Because if you have a single determinant, the on-top pi density is telling you, well, you can't have two alpha in the same place. You can't have two beta in the same place, but you can have alpha and beta in the same place. So the on-top pi density is actually measuring spin in some ways. It is giving you about the same information as the spin did before, but using this formula, you don't break bond breaking. Bond breaking is working perfectly fine. So you can use this formula to basically reproduce the one determinant behavior of quantum DFT, but while keeping the multi-configurational behavior that you want, which is bond breaking is correct, all the triplet components are the same, and everything like this. And this dates from 1991 initially, but most people know the version from Limani and all from 2014, which is in Molcast. And this year we proposed for the first time a variational version. And this variational version now satisfies absolutely all the properties that we want. So it is variational, that's obviously one thing. It is equivalent to quantum DFT for one determinant. You can perfectly justify it in terms of, like it is fully exact for a full CI expansion in principle. And it does bond breaking, spin, and no double counting. And as I said, we have implemented this ourselves in my code called multiPsy. And this is extremely efficient. So you can see we for the first time could do an entire protein with MC-SCF calculation. And you can see the cost of the MC-PDFT just basically becomes the same as DFT. It's actually slightly cheaper because DFT you have to do unrestricted, and you have to have two densities to compute. So it's a bit more expensive. So this is basically, this MC-PDFT is as expensive as DFT. You have essentially no reason not to use it if you need it. And the good thing with now this PDFT as a new framework is that first you realize this cast by DFT, that's just MC-PDFT. It's a different name, but it's the same thing. It's a function of the density and on-top density. So that is already just a hybrid MC-PDFT with 100% MC-SCF energy. And all the other ones that were not MC-PDFT, if you turn them into MC-PDFT, you fix all the bottom properties. So now you don't have to compromise between bond breaking and spin. You just replace the DFT part by a pair density part, and suddenly everything is fixed. So now I have improved all of these schemes for basically no extra cost. And that's why I'm in now by this universal framework. So now by using MC-PDFT, we have unified all of these schemes under one and improving them at the same time. So now we can start actually benchmarking them, comparing them for the first time in the same systems. And we have a list of functionals. So MC-PDFT gives us the pure functional. So I use all functionals of the blib family so that we can compare similar things. And so they have all a little t to basically say what translated, but otherwise it's just blib. So MCT blib. Then MC-SCF plus DFT is just MC-SCF plus the t lib correlation functional. This one, cast by DFT, we just use whatever they have designed. And then we translated TB3 lib for this hybrid, and we have a range-separated version of blib. So again, we use same functionals so that we can compare them nicely. And now we will compare them on 3 different cases: spins, double counting, and dissociation. And for the spin, we have this small organic singlet triplet gap benchmark, which contains both molecules which follow the Hund's rule, meaning that the triplet is lower than the singlet, and those which don't, which means that the open shell singlet is lower than the triplet. And these are the results. And the first thing that obviously stands out is that this cast by DFT functional is not doing very well. And that's because of the spin that I mentioned before. So both this functional has a on-top density dependency, which is in blue here. And so for one, that's an on-top density which corresponds to the one single determinant Hartree fork. And so this is just one, so it just gives you back the lib functional. But of course, as the density gets lower, meaning that you have more and more correlation, the correlation is scaled down. So the DFT correlation is scaled down, as you would expect. However, when the on-top density goes smaller, it also could be because of the spin. Because as you increase the spin, the on-top density also goes down, because if you have all alpha electrons eventually, density is 0. The on-top density is 0. And the correct behavior for that, that's the gray and green curve. That's the one that you get from translating the spin densities. And they are very different. So if you're trying to make a functional which removes double counting, it's also destroying all your spin properties that you had before. So this basically always favors the open shell singlets compared to the triplets, because you have strong correlation for open shell singlets and very little for the triplets. And that's why you have this large error. Except for that, we can look a bit more closely at things. You see that there is very small, so we use 2 different active space, one which is just 2 orbitals, which is all you need to describe a triplet, and one which is the whole pi system. And you can see that there is not much dependency on Hund type molecules, but there is a bigger dependency on the anti-Hund. And in general, the anti-Hund, we don't describe it correctly with only 2 orbitals in the active space. You actually need to have the full pi system in there to get the anti-Hund behavior correctly. And all the hybrid functionals actually do that correctly, which is very nice because it's actually difficult to predict in DFT. This anti-Hund behavior is very hard to find in DFT. So we have one scheme where we actually get it correctly. Otherwise, if I combine the Hund and anti-Hund and I sort of look down at the result, you can see that the pure functional has basically no active space dependency. It's very little. And that's one of the most appealing properties about it, because that means we don't need to use large active space to describe the system. But the best results are for this TP3 leap and TSRB leap. For double counting, I took a small molecule where I can increase the active space to full CI, and I took B2, binding energy. And B2 is also nice because it actually has strong correlation also. And I think I need to go a bit quicker here, but you can see that MCSCF, as you increase the active space, goes towards the reference, not fully because it's only double zeta, but gets close. And very strong active space dependence. On the other hand, the translated B-leap, so the pure DFT, has basically no active space dependence at all. It's the same result at all time, but it slightly overbinds. And so like in ConSham, we know that pure functionals are just not enough. We need to go to hybrid. On the other hand, if you use this MCSCF plus DFT, you just add correlation. You're just shifting up the entire curve. So you're improving for small active space, but for large active space, this orange curve is clearly getting too far. And that's this double counting effect that we're talking about. Interestingly enough, this HPG20, which is supposed to correct that, doesn't do a great job at it either. And finally, what we see is, again, the best results are for these 2 other hybrid type, where for the small active space, it's not quite there yet, but for the full valence one, you're already at the pretty much converge, and there is no double counting. And finally, the most difficult case we might think of is chromium dimer dissociation. And of course, any talks about strong correlation has to mention that. And so this is the result. And it's a very interesting case because there is strong correlation absolutely everywhere, but there's also a lot of dynamic correlation. So if you just do MCSCF, you might be fixing strong correlation, but you're still very far off, and you actually barely predict it in binding. And what you can see is that, again, the pure PDFT overbinds. So they all dissociate correctly, which is nice, but pure PDFT overbinds. On the other hand, if you have this MCSCF plus DFT, which might have double counting, yes, but it's still clearly not enough here. And that's very similar to what you do in normal DFT. You can't have just a functional which works well with 100% artifact exchange. It's very difficult to do that. DFT exchange doesn't describe just the exchange. It describes some correlation. So you need to put it in there to get the right result. And so at the end, the best answers are, again, these 2, TB3 leap and TSRB leap. TSRB leap technically gets a better binding energy, but the shape of the potential is a bit better with TB3 leap. And some people among you might look at this and say that TB3 leap star might be the correct answer. It should be slightly lower here. Anyway, so quick conclusion. Basically, this PDFT does exactly what you want from it. It extends DFT to multiconfigurational method. And that means that most of the behavior actually looks very much familiar to what you would expect from normal ConSham. So pure functionals, they are quite amazing in terms of cost and in terms of active space dependency, but they are ultimately insufficient, exactly like in ConSham. Adding MCSCF plus DFT, not only you're double counting, but also you're just exactly like a 100% artifact exchange functional, you're not good enough. And avoiding double counting by using this density-dependent behavior is just not working because it destroys the spin behavior. So at the end, the 2 best functionals are the one which are global hybrid with about 20% MCSCF or range separated. And global hybrids technically have some double or undercounting, but it's very small due to the lambda square scaling. But the main conclusion really is that most multiconfigurational variants that have been proposed throughout history can actually be reframed under this MC-PDFT framework. And because of this, I think we can now try to move on and stop designing new scheme and instead try to figure out how to design new functionals. And in particular, new functionals which depend explicitly on the density function. So I would like to thank my group and my collaborators, and of course, thank you for your attention. Give up this time. Yes. Yes. That's the reference I'm using. I'm using the revised.
That's what you call the experimental curve?
Yes.
Okay,
so it's experimental reinterpreted with theory.
Good, because that was my comment.
Yes.
And then a naive question, like how does all of this tie to what Don Schuler and Laura have done?
Yeah.
Don't they also call it MC-PDFT?
So it is the same scheme. It's the same formula of energy expression, but they don't do it variationally.
Oh.
They just do MCSCF first and use these orbitals and these CI coefficients to compute the density and entropic density. And that makes quite a big difference. First, because I think it's nice to be variational for properties and whatever, but also because if you don't have the correlation in your optimization of your wave function, you're missing quite a lot on the relaxation behavior. So somebody might converge to the wrong ground state because with correlation, the ground state is different. And in general, like they have then a lot of things that they have added on top of that to try to relax this. So they have this multi-state PDFT, which is basically trying to re-optimize the wave function by rotating them in between. Like, there's other things that are trying to just sort of fix this fundamental issue that they don't have correlation to optimize the wave function in the first place.
Okay.
So yeah.
Can I ask like a follow-up question?
Yeah, quick.
So you had this B2 curve.
Yeah.
Okay, so the MCSCF result, so along the x-axis you had the active space, right? So why doesn't the MCSCF result give you full CI?
So because my reference is not the full CI in that basis. It's the correct result in ideally infinite basis. So MCSCF is just double zeta in this case.
Okay,
so it's not getting quite there.
Okay.
And of course you would expect PDFT to have a smaller base set dependence than MCSCF, or than full CI rather.